Lesson 20 is inverses of functions, and first we're going to learn how to find the inverse relation to a function. So there's 3 steps to this process. Step number 1 is going to be to change function notation, like changing f of x to y. We know that f of x and y are interchangeable, and for these types of problems we want to deal with y as opposed to f of x. And then step 2, switch the places of x and y, so that means like literally just swap their location in your equation. And then step 3 is to solve for y, and that means to like get y completely by itself to isolate it. So example 1, find the inverse relation for f of x equals 3x plus 6. So step 1 is to change function notation. So change f of x into y equals. So it'll be y equals 3x plus 6. And then step 2 says to switch the places of x and y. So that means they're literally just going to like change where they're located in the equation. So it'll start with x equals instead of y equals. So it'll be x equals, and then instead of 3x, it'll be 3y plus 6. And then step 3 is to solve for y. Step 3 usually kind of involves like kind of 2 steps within it, or at least 2 within it. But we want to get y by itself. So to do that, we have to use inverse operations. So there's a 3 that's being multiplied by the y and a 6 that's being added. So first we'll cancel out the addition of, or like adding 6 by subtracting 6 from both sides. Usually we want to undo addition or subtraction first. It makes life a little bit easier. So we'll cancel out that plus 6 by subtracting 6 from both sides. So then I have on the left side of the equal sign x minus 6 equals, and then I'll bring down my 3y. And then my goal for this step is to just get y completely by itself, so I still have some work to do. I have a 3 that's being multiplied by the y, so to cancel that out, I'll divide both sides by 3, since division is the opposite of multiplication. The 3 divided by 3, that'll cancel out, so that'll leave me with just y on the right side of the equal sign, like we wanted, just y by itself. On the left side, I have to kind of treat this in 2 parts, so I can do, this is like x divided by 3. Remember, if we don't have a like number in front of a variable, it'd be a 1x. So this is like 1x divided by 3. So think of it as 1 divided by 3, so that's 1/3, and then the x just tags along to the end. And then after that, we have to do negative 6 divided by 3. So negative 6 divided by 3 is negative 2, so that becomes minus 2 after the 1/3 x. So when you have, this is called multiple terms, like inside, or in the numerator, the x is one term, the negative 6 is another term. If you have multiple terms in the numerator, you divide both of them by the number in the denominator. So that result is 1/3 x minus 2. And then now we just want to write the equation with y on the left side of the equal sign. It's a little bit more standard. So it'd be y equals 1/3 x minus 2. So y equals 1/3 x minus 2. And then over on the right of the page, there's an input-output table for both the original function, f of x. So f of x equals 3x plus 6. Over here, this is f of x equals 3x plus 6. That's the input-output table for that function. And then there's also the input-output table for the inverse that we just found. So it's y equals 1/3 x minus 2. We want to kind of notice a like relationship between the 2 tables. So if we look at each point one by one, on f of x, the first point is negative 1, 3. And on our inverse, the first point is 3, negative 1. So they have the same 2 numbers, but they just switched locations. They switched to input and output. So remember, on the table, the input is like your x's. That's the numbers on the left side of their left column of the table. And then the f of x or y is the output. That's the numbers on the right column. So x is our inputs, y's or f of x are outputs. If we look at the second point on the table, on f of x, it's 3, 15. On the inverse, it's 15, 3. So same 2 numbers, just switch locations. And then on the third point, or in the third point, it's 10, 36, and then for the inverse, it's 36, 10. So hopefully you're kind of seeing the trend of like each of the inputs and outputs are switching, and that's always going to be the case for any function and its inverse. The input and the output of a function and its inverse will switch. So this was my input here. It became the output of my inverse, and then this was the output of my original function, and it became the input of my inverse. Okay, example 2, find the inverse relation for f of x equals 2/3 times x plus 3. So we're going to follow actually those same set of steps up here, so I'll try to keep them like in view. So step 1 is to change function notation, like take out the f of x and put a y there instead. So it'll be y equals 2/3 and then times x plus 3. And then step 2 says to change switch the places of x and y. So y is right there, x is right there. We literally just want to like swap them out for each other. So instead of starting the equation with y equals, it'll start with x equals. And then everything else will stay the same. So it'll be 2/3 and then times y goes in for x plus 3. So the numbers don't change in this step. You're really just switching x and y. And then step 3 says solve for y. So y is right here. Solving for it means to get it completely by itself. So with this equation, there's a couple different ways that we can do it. One method is to distribute in that 2/3 to get rid of the parentheses, but you don't necessarily have to do that. I don't know how much we've done this so far this year, but I'm going to show you guys how to cancel out the 2/3. I'm going to go ahead and zoom in since we're on step 3, so there's no more like kind of new steps to write down. So if I want to isolate y, I have to get rid of the parentheses, which means I have to get rid of this 2/3 because that 2/3 is supposed to be multiplying by the entire parentheses. So what I'm going to do to get rid of that 2/3 is I'm going to multiply by its reciprocal on both sides. So you can write, actually let me backtrack a little bit. So reciprocal is like a fraction flipped upside down. So the reciprocal of 2/3 would be 3/2. So I'm going to multiply by 3/2 or 3/2 on the left side. And then I would multiply it on the right side as well. And you can write it like if you don't have room, you can write it off to the side here. I'm going to put it just like directly inside here because I have a little bit of space. But I'm multiplying a 3/2 onto both sides of the equal sign. Okay, so now what this does is if I multiply any fraction by its reciprocal, they multiply together just to get 1. So they essentially like cancel each other out in terms of multiplication. So 2/3 times 3/2 is just 1, but I don't have to write that 1. I can just bring down the y plus 3 that was inside parentheses up here. And since there's no longer a number other than 1 in front of the parentheses, I don't need the parentheses anymore. So technically, like I could write like 1 times everything inside the parentheses, but anytime you multiply by 1, it doesn't change the value. So that's why it's okay to just leave the 1 and leave the parentheses off here. And then on the other side of the equal sign, I have 3/2 or 3/2 x. I'm just going to write that down. So 3/2 x. And then now the parentheses are gone, so we're like pretty close to having y by itself now, or y isolated. Now I just have that plus 3 that I have to cancel out. So opposite of adding 3 is subtracting 3, so I'm just going to subtract 3 from both sides. And then when I do that, this will be a 3/2 x minus 3. So 3/2 or 3/2 x minus 3. And then equals over here, the 3 minus 3, those will cancel out and just leave me with y by itself on the other side of the equal sign. So I have 3/2 x minus 3 equals y, and then I just want to rewrite it so that the y is on the correct side of the equal sign. Not that it's incorrect, just like a little bit more standard to have it on the left side. So it'll be y equals 3/2 x minus 3 is my inverse. Okay, so whenever you have a fraction that you need to cancel out, you can multiply by its reciprocal, and any fraction times its reciprocal is always going to equal 1. So it's kind of like a shortcut rather than having to just go ahead and like distribute in the 2/3. I think that would have taken a little bit longer. Okay, next section, determining if an inverse is a function. So the first example of this section says find the inverse of f of x equals x squared. So same set of steps. I'm not going to scroll back and forth just because it'll make the screen a little crazy. But step 1 is to switch out f of x for y. So it'll be y equals x squared. And then step 2 is to switch the places of x and y. So then that'll become x equals y squared. And then step 3 is to get y by itself, or to like solve for y, isolate it. So that y squared, the thing that I need to do to get y by itself, if I have to like cancel out this exponent, the opposite of squaring something would be square rooting something. So I would have to take the square root of both sides, and that would cancel out the exponent, and it would leave me with just y, which is what I want. So I have y by itself. And then when I'm solving and I take the square root of something, I typically include like the positive and negative version of that. So instead of just the square root of x, I'd write it as the positive and negative square root of x. So my inverse would be y equals positive or negative square root of x. Okay, so now we're going to analyze the graph of both the function and its inverse. So the original function, f of x equals x squared, that's the red line, the one that's like a U kind of opening upwards. And then the inverse is the blue one. So y equals positive or negative square root of x, that's this one right here. So go ahead and draw the sketch and then label them. So actually you can leave the labels off right now. So in order to kind of check whether or not something is a function on the graph, we use something called the vertical line test, which we studied maybe a few months ago at this point. But the vertical line test can always be used if you have a graph in front of you. So what it is you either like in your imagination or like physically, you can grab a vertical line, you can grab a ruler, you can grab anything that's vertical and drag it across your graph. And we're just going to focus on one at a time. And what we're looking for at the vertical line test is to see if the vertical line crosses at more than one point on the graph at one time. So we'll just focus in on only the original function for right now, so only the red one. So if I drag the vertical line across, it's only ever touching our original function, the red one, at one point at one time. So it's important to just kind of try to ignore the blue one for now and focus only on the original function, the red line. It's only touching it at more than one point at one time. So that vertical line test is just kind of proving that our original function like is in fact a function. And then we can use that vertical line test on the inverse as well. So our inverse is the blue line. It's this one down here. If I drag a vertical line through it, you can see it definitely hits on our inverse at more than one point at once at several different locations, like almost the entire graph it's hitting at more than one point at one time. So that means that our inverse is not a function because it fails the vertical line test. So if it does cross at more than one point at one time, it fails the vertical line test. So it's not not a function. So we'll say inverse is not a function. Okay, so you can kind of see, well, like just based on the wording down at the bottom of the screen, that there is kind of a shortcut to determining if a inverse will be a function, and this is when we don't actually have the inverses graph. So I'm going to erase and kind of draw off of this graph up here. So if you notice, like the original function and its inverse, they're like the same shape, but they're just kind of like pointing in a different direction. And that's because functions and their inverses are going to be reflections of each other over the line y equals x, which is that pink line that I just drew. So if I took my original function and I reflected it over that line, it would end up looking like the inverse. So there's a shortcut that you can use just based off of the original function to check to see if its inverse will be a function, and that's like kind of like the opposite of the vertical line test, and it's called the horizontal line test. So the shortcut for determining if the inverse will be a function, use the horizontal line test on the original function. to determine if its inverse will also be a function. So if you have the graph of the inverse like we did up here, it's fine just to stick with the vertical line test. If you only have the graph of the original function, but you're asked, hey, will its inverse also be a function? Then you use the horizontal line test, which is kind of what it sounds like. It's the horizontal line instead of a vertical line. So if I take my horizontal line and I drag it through my function, it crosses at more than one point at one time. And that means that the inverse will not be a function because it failed this test. So inverse will not be a function. Okay, I'm going to kind of zoom out and look at this as a whole. But like I was saying, so the vertical line test is when you're checking that exact graph. The horizontal line test is for when you're checking to see if the inverse of your graph will be a function or not.